Hello. My name is Mohammad Matinbostan Sara. I'm 29 years old. I'm from Iran, from the city of Hamadan. I'm a student in the artificial intelligence program at the major company I learn. And today I want to talk to you about a truly remarkable invention, an invention that was profoundly inspired by some very special people in my life, individuals for whom no effective cure had yet been discovered, meaning no one had been able to successfully come up with a viable way for them to genuinely return to a normal, healthy life. I was thinking of people who had suffered from significant spinal cord injuries, extensive spinal cord damage, or complete paralysis of various parts of their bodies, such as their lower limbs like legs, their upper limbs like arms, or even from the neck down. Additionally, I considered those who had tragically lost a limb, for instance, a hand or a leg. This made me start thinking about coming up with something, an idea, which actually already exists in the world today. But what I am doing is bringing an innovative approach to this idea, an advanced neural system to bypass spinal cord injuries and control prosthetic limbs, and even to give those prosthetic limbs a sense of touch. This invention is applicable in the fields of neuroscience and biomedical engineering, smart prosthetics, and brain-machine interfaces or BCIs. Its goal is to re-establish the connection between the brain and paralyzed or even amputated limbs. By using neural interfaces and advanced electrode technologies that exist, we can make this possible. In cases where the spinal cord is severed or damaged, and the movement commands from the brain can no longer reach those limbs that have lost their connection to the spinal cord. And also, if a limb is amputated, we cannot simply replace it with a mechanical prosthesis alone. It is not connected to the spinal cord, and also, if a limb is amputated, we cannot simply replace it with a mechanical prosthesis. This task in physics requires a system that can directly receive neural information from the brain and transmit it across the damaged or severed areas of the spinal cord. It can deliver signals to paralyzed limbs such as the hands and feet, and even restore sensory information like pain, heat, pressure, cold, and so on. We can divide this into three sections. The first part of the brain neural interface involves ultrafine electrodes or non-invasive chips that allow us to read the signals coming from the brain. Those signals are analyzed using artificial intelligence patterns, and we use them to detect our immediate intention to move. The second unit is the spinal bypass interface, which is a central processor that receives the brain signals, decodes them, and sends them directly to the paralyzed or artificial limb. In cases where the spinal cord is damaged, it bypasses the injured or severed section of the spinal cord, ignores that part, and sends the signal to the peripheral nerves located below, reaching deep into the limb that is, so to speak, paralyzed or amputated, for example. And for a prosthetic limb, we absolutely needed to be able to accurately sense various crucial things like the delicate feeling of touch, the sharp sensation of pain, the distinct differences between heat and cold temperatures, and varying degrees of pressure as well. An electromechanical prosthetic limb equipped with a neural interface that connects to the body and its outer surface is covered with a biocompatible silicone layer similar to skin. This silicone outer layer is capable of transmitting sensations of touch, heat, cold, and pain. The innovative features we have introduced include the combination of BCI, bypassing spinal cord injuries, and precise control of movements in the prosthetic limb. We have incorporated a sensory feedback method on the surface of the artificial skin, as well as the use of machine learning to adapt to specific commands for each individual. Thank you.